Now that you've learned about the concepts of span and linear independence, we can learn about basis vectors. So the basis for a space is a set of linearly independent vectors that spans that space. So in the example we've been working with, we already know x and y are linearly independent and span all of 2D space, so they are a basis for 2D space. And that means that we can write any point of that space in terms of these two vectors. So if you know what x and y are, I can give you a and b and you instantly know what point in all of 2D space I'm referring to. And we'll see that in a few minutes. It turns out that you've been using a basis all your life, maybe without knowing it. When we define a coordinate system, we're often defining it with respect to some standard basis. So in the case of 2D space, our standard basis is E1 and E2, where E1 is 1, 0, and E2 is 0, 1. We have equivalent standard bases for R3, R4, and so on. So what this means is when I give you a vector and its coordinates 2, 3, what I'm actually telling you is that x is a linear combination of the standard basis vectors, where the weights are 2 and 3. So x is 2 times E1 plus 3 times E2. So we often use a standard basis. It's the default, I would say. But we can use lots of other bases. So let's say now that we have a different set of basis vectors, v1 and v2. We can write x as a linear combination of those vectors. So in this case, x is 2 times v1 plus 1 times v2. And so we can now define x with the coordinates 2, 1 with respect to this new basis. So x hasn't changed, but the coordinates we use have because they depend on the basis we're using. And this is what we're doing here is a change of coordinates between two bases, and you'll see that much more in depth later in the course during the dimensionality reduction day in the Comp Neuro course. For now, I just want you to mostly take away the intuition that there's multiple different basis vectors we can use. So I've been talking a lot about spaces, and I haven't really formally defined what I mean by that. So I've actually been referring to a pretty formally defined concept, which is a vector space. Two-dimensional space is a vector space. Three-dimensional space is a vector space. Any dimensional space is a vector space. But we can have other vector spaces. A vector space is a set of vectors closed under linear combination. That's a little technical, but basically what it means is that any linear combination of any vectors in that space has to also be in that space. So a one-dimensional line in 2D space is also a vector space. But not always. So with this one-dimensional line, it's not a vector space. And the reason for that is that if you have a vector going from the origin to a point on this line, and you multiply it by 0, you'd get the 0 vector at the origin. So that's a linear combination of a vector in the space. But the origin is not in the space. It's not along this line. So this is not a vector space. So your vector space has to always include the origin. I will go into a more formal definition of a vector space in the bonus materials. And I'll also go through a couple examples of more unusual vector spaces to try and highlight what we actually mean by vector space. In this course and in general in neuroscience, you'll mostly be working with real valued number spaces, so all of these full spaces and also all subsets of spaces like a 1D line through two-dimensional space, or as you'll see in the next exercise, a two-dimensional plane through 3D space, and so on. So next, you will apply the concept of basis vectors to new spaces, and you'll connect this with ideas about the dimensionality of the space. And specifically, you're going to connect the change of basis to a beginning concept of dimensionality reduction, although you'll of course dive much more into that later in the course during the day devoted to dimensionality reduction. So in particular, you're going to be identifying properties of a basis for this 2D plane in 3D space.